Today I'm going to present my term project paper on classification for PlantDoc using DNN models. To get started, let's view at the high level of our project. So first we have downloaded the dataset from an open source software, and later we have converted these images into 416 cross 416 image size to maintain a consistency of images along all the images so that we can use these images for training our model. Later, we have read this data into a NumPy model along with the labels associated with each of the image, which can be used for classification of those images for the model. Later, we have applied Gaussian blur on this each image. The reason being we have applied Gaussian blur is to increase the region of interest and reduce the background noise. Later, we have applied data augmentation as well. The reason for data augmentation is the images in each classes are ranging from 75 to 175, which is a small number for any DNN model to train for a particular class. So to avoid underfitting, so we have applied data augmentation, which increases the number of images for each class and enhances the classification possibilities for a model. So later we have selected three main models for our classification. One is the ResNet, then we have used Inception V3 and a custom CNN model. We have applied hyperparameter tuning for these three models with different parameters like epoch, batch size, learning rate and others. Later we have selected our best model out of these three models using the accuracy, precision, recall and different parameter evaluation metrics. So the best model we found was Inception. So let's look at the code. Before that, let's see how are the images. These are the different 6 images randomly picked along with their classes on the top. So these are the different images along with leaves, and we are going to classify these images for their classes respectively. So let's look at the demo. So first we have downloaded the dataset and we have stored it into our Google Drive. Later we are trying to read for these particular classes. So these 17 classes, we are going to read the dataset. The dataset has been already classified into two main structures, two folder structures. One is a train dataset, another one is a test dataset. So first let's read the train dataset. In this function, we are going to resize the image along with normalization of the image to maintain a consistency, and later we are going to append a label to it as well so that we get the correct class for it. So the similar process has been applied for training and testing, and we are saving this data into our output path. Now we use this output path for the training data set and we start our pre-processing methods. So this is the pre-processing mechanism. So first we look at the random images out of this. These are the 6 random images, and later we can see the distribution of the classes. We have only from 75 to all the way till 175. So this less number of data set for each class is the reason we have applied data augmentation in the later stage. So once we get the dataset, we are going to split the dataset into two main things. One is the training dataset, another is the validation dataset, which is used for the model to validate against this validation dataset. Later, we are applying Gaussian blur on both training dataset and validation dataset. So the Gaussian blur is to remove the noise in the background. So if you see the image, the leaf is been highlighted and the background is been blurred after applying Gaussian blur. This dataset has been saved so that this can be used for faster training in the later stages instead of applying pre-processing for every model. Now let's look at the model running. So first let's look at the ResNet model. So first we load the dataset which has been pre-processed from our path. Later we use the image generator. So this is what I was mentioning. So we are using image generator to generate images for a similar class. So the first image we are generating images based on different rotations of the image. So the image has been rotated at a 20 degrees interval, and later we are doing a horizontal shift and a vertical shift of 0.2, 0.2, and we are doing a zoom range of 0.2 in and out, and these kind of different parameters have been applied for the image generator. So, and these are the hyperparameters which we are using. We are using an epoch of 25 and a batch size of 8 for this ResNet. So first let's download the model, the ResNet model from the Keras inbuilt. We are using a pre-trained weights of ImageNet so that the model has a starting point to train its model. Once we get the image, we are applying a softmax layer in the end so that the model can classify based on the different classes which we have labeled it for. So once we are also applying checkpoint mechanism. This is because we want to save the best model out of the 25 epochs. So in 25 epochs, if the 15th epoch is better, we want to save that model as well. So later we compile the model and then we fit the model with the hyperparameters which we have trained along with the training and the validation dataset which we have created. We save this model into our output path, and if we see the history of the path, how it is saved and how the accuracy and validation changed over a period of epochs. Once the model is trained, we load the model and we test it against our test dataset, which has not been pre-processed. It's a plain dataset. Now when we test the dataset against the testing dataset, we have achieved an accuracy of 89.5%, which is a good accuracy. But as accuracy is not only the parameter which determines the model ability, we also determine the model accuracy by other scores like other metrics like F1 score precision as well. So if you see at the confusion matrix which is plotted here, the heat map of true positives are much higher here than the true negatives, which is less. And even the precision and the recall from the classification report states this. So you can see that the precision is pretty much high. For some classes it may be less, but most of the classes the precision is pretty much good. Now let's go for the inception model. Similar to ResNet model, we have gone for the inception model. We are training our dataset based on the images which we have pre-processed already. And later we are applying an epoch of 20 and a batch size of 8 with 416 as the input image. The image generator is similar to as the ResNet. So the reason being the same reason, the dataset is small. So that's the reason we are applying image generators. We are applying checkpointing. Here also for inception, we are applying an ImageNet weights for the model to have a starting point here as well. The softmax layer in the end, the dense softmax layer is fixed to classify the model. This is the summary of the model along with the parameters, weights. Later we fit the model. Now when we fit the model, we see some anomalies here, but the model eventually has a good accuracy over a period of epochs. So once we train, we download the test dataset again, we load the test dataset and we check the accuracy. So we see that the accuracy for the test dataset for this inception model after training is 61%, 61.4%. So if you look at the confusion matrix here, we can see more true positives than the ResNet here. There are very less false positive, which is minimal, and it is in a closed class and it's less. Then if we look at the classification report as well, the precision and the recall scores are much higher than compared to the ResNet model. Now let's look at the custom CNN model. Custom CNN model was designed by us. It doesn't have any prefixed structure. So the model was designed in this fashion, which consists of different convolution layers, batch normalizations and max pooling layers. So at every layer, it started from 256 as the first convolution layer, followed by a batch normalization and a max pooling for every two layers. So every 2 layers of convolutions was sandwiched between a max pooling layer and a batch normalizations. And in the end, we have a dense layer. We have a dense layer which is of softmax to classify them for the model to classify based on our labels. So this is the structure on a high level, how the model has been, output shape and the parameters which are used for this model. So we have again used image generator in a similar fashion along with the checkpoint in a similar fashion as the ResNet and the inception. Later we are using Adam optimizer for all the 3 models which I have not mentioned, and the matrix is accuracy matrix, and we are going to fit the model. Once we start fitting the model, we can see the graphs. Compared to the ResNet and inception, we don't see the graphs converging at any point over here. They're far apart, but they're hugely less accuracy when compared to the previous one. Now let's look at the test dataset and what's the accuracy. You can see that the test accuracy is very, very minimal. So this can be couple of reasons. One, the structure of the model is not properly designed for the PlantDoc detection, or it can also be because of the pre-trained weights which we have used in inception and ResNet. which is of the ImageNet. So, and if you see it, look at the confusion matrix heat map as well. There are many false positive cases than the true positive cases. There are very minimal true positives. Maximum are outside the correct classification range. And even the precision and recall scores are very, very minimal, which is a bad sign and not good model. So on a conclusion level, I would like to say that Inception gave us better results and a better model, which was used for PlantDoc detection. So we can much more, the future scope of this project would be to enhance this custom CNN model, develop a custom CNN model, a small CNN model, which is more capable of classifying PlantDoc with a higher accuracy and more precision. Thank you.